Africa has one of the fastest growing populations in the world. According to the projections of the United Nations, the continent's population is expected to continue growing rapidly throughout the coming decades. Meanwhile, the electricity demand is expected to increase dramatically by 2050. And this is not surprising, because industrialization, urbanization, and economy growth all require energy. Simply said, more development equals more energy consumption. Africa possesses major energy resources: coal, natural gas, oil, resources that could theoretically be used at scale to power the continent's development. But here's where things become interesting. Many African countries are signatory of the Paris Climate Agreement and have committed to reducing their greenhouse gas emissions over time. This means that while fossil fuels are still available, there is an increasing pressure to develop cleaner sources of energy. So, if the long-term objective is to reduce the use of coal, oil, and natural gas, what options remain? Can all Africa's future energy demand be supplied using only renewables? This is exactly the question we'll try to answer in this video. My name is Ken. You're watching the African Grid. On December 12, 2015, representatives from countries around the world gathered in Paris and adopted what becomes known as the Paris Agreement. The objective was simple in principle, but extremely ambitious in practice: limit global warming and reduce long-term impacts of climate change. One of the main goals of the agreement is to keep the increase in global average temperature well below 2 degrees Celsius, while pursuing the efforts to limit it to 1.5 degrees Celsius above pre-industrial levels. This is why renewable energy has become such an important topic across the entire continent. Now the question becomes, is a 100% renewable electricity grid technically possible? What could such a system actually look like? And what challenge will need to be solved in order to make it work? To answer these questions, we first need to understand how an electrical grid operates. The electrical grid is basically the highway system of electricity. Its job is to ensure efficient, renewable, and affordable transport of electricity from where it is produced to where it's consumed. Generally, the electricity pathway can be separated in major steps. At the first step, we have the generation. This is where the primary energy is converted into electricity. Here, we basically deal with coal power plants, gas power plants, hydroelectricity dams, nuclear power plants, and increasingly large-scale solar and wind farms. Each generation technology operates according to different engineering principles. Now comes the transmission. After electricity is generated, it must often travel hundreds and sometimes thousands of kilometers before reaching the end consumers. In order to make this efficiently possible, electricity is transferred at very high voltages. The reason is simple. Power losses in transmission lines increase with the square of the current. Therefore, by increasing the voltage, the current can be reduced for the same amount of transmitted power, resulting in lower transmission losses. The grid is typically divided into several voltage levels: extra high voltage, medium voltage, and low voltage level. The devices responsible for moving electricity efficiently between these different voltage levels are called transformers. And then we have the necessity of having real-time balance between supply and demand. In fact, unlike water, coal, or natural gas, electricity can not currently be stored economically in massive quantities across an entire continent or even across an entire country. Although battery technology are improving rapidly, large-scale storage remains one of the major engineering challenges of modern power systems. And exactly for that reason, electricity production and consumption must remain perfectly balanced at every moment. Every second, every minute, and every hour, grid operators continuously adjust generation to ensure that supply matches demand. And this is where one of my personally favorite concepts in electrical power systems come into play: the grid frequency. You can think of frequency as a kind of thermometer for the electrical grid. It tells us whether the system is in balance or not. In most African countries operating synchronized AC grids, the normal frequency is 50 Hz. This frequency is directly linked to the rotational speed of large synchronous generators connected throughout the network. If a large industrial consumer suddenly connects to the grid, additional power is immediately required. Before generators have time to respond, this energy is temporarily extracted from the rotational energy stored in their spinning masses. As a result, the generators slow down slightly and the frequency drops. The opposite can also happen. If instead a large generator suddenly disconnects, frequency may decrease because generation becomes insufficient. All generators connected to the synchronized grid are electrically linked. These frequency changes can then be detected hundreds or even thousands of kilometers away from where the disturbance occurred. So grid operators constantly monitor frequency because it provides one of the clearest indicators of the health and stability of the entire power system. How all these disturbances in the grid frequency are managed is a fascinating topic on its own. If you would like a dedicated video on frequency control and grid stability, just let me know in the comments. Now that we've understood how an electrical grid works, we can return to our original question, which is, can Africa build a power system based entirely on renewable energies? From a technical perspective, many experts would argue that the answer is yes. However, making such a system work perfectly and reliably will introduce a really huge amount of engineering challenges. The first one is intermittency. Unlike conventional power plants, renewable energy sources cannot always produce electricity whenever we want. Solar energy depends on sunlight. Every day, solar production falls to zero after sunset. Cloud cover can also significantly reduce production. Wind energy faces a similar challenge. Wind turbines only generate electricity when sufficient wind is available. Some days may be extremely productive, while others may generate very little electricity. The second challenge is inertia. Earlier, we discussed frequency and how it acts as the thermometer of the electrical grid. Traditional power plants, such as coal, gas, hydroelectricity, and nuclear facilities, contain massive rotating generators. These rotating machines store large amounts of kinetic energy. When disturbance occurs, this stored energy helps stabilize the grid by slowing down the frequency deviation. This phenomenon is called inertia. Many renewable technologies, particularly solar photovoltaic systems, do not naturally provide the same level of physical inertia because they are connected through power electronic converters. As renewable penetration increases, the behavior of the grid changes. Frequency can move more rapidly after disturbances, making system operating more complex. Engineers are currently developing solutions such as synthetic inertia and advanced inverter technologies to address this challenge, but it remains an important consideration for future renewable power systems. Another major challenge is maintaining the balance between energy production and the consumption. In fact, electricity demand changes throughout the day. People wake up, factories start operating, air conditioners switch on, industrial facilities increase production. All of these activities influence electricity demand. At the same time, renewable generation may be increasing or decreasing independently of consumer behavior. This literally means that even if enough renewable energy is produced for the entire year, operators must ensure that the electricity is available every minute, every second, every day. And this brings us to one of the most important requirements of any highly renewable grid, the energy storage. When solar and wind production exceed demand, excess energy must be stored somewhere, so that when production falls below demand, that stored energy can be released back into the grid. The larger the share of renewable energy becomes, the more important storage systems become. This is one of the reasons why battery technologies have received enormous attention in recent years. However, it is important to remember that utility battery deployment remains relatively new. And although battery projects are growing rapidly around the world, storing enough electricity to support entire national grids for extended periods remains a major engineering and economic challenge. Fortunately, we are not starting from zero. Several technologies exist that can help solve their challenges. The most widely discussed solution today is battery storage. Large battery installations can absorb excess renewable energy during periods of high production and release it when needed. One famous example is the Hornsdale Power Reserve in Australia. It's one of the world's most well-known grid-scale battery projects. Another solution is pumped hydro storage. The principle is relatively simple. When electricity is available, water is pumped uphill into a reservoir. Later, when electricity is needed, that water is released through turbines to generate power. In many parts of the world, pumped hydro remains the largest form of energy storage currently available. A well-known example is the Drakensberg pump storage system in South Africa, with the installed capacity of 1000 MW, capable of storing up to 27.6 GWh of electricity to help stabilize the grid. One other powerful solution involves connecting countries together. The larger the grid, the easier it becomes to balance renewable generation. A cloudy day in one country may be compensated by strong winds in another. One region may have excess hydropower while another region has excess solar generation. This is why initiatives such as the Southern African Power Pool and the East African Power Pool are so important. By sharing electricity across borders, countries can improve reliability and reduce overall system costs. Finally, there are smart grids. Modern sensors, communication technologies, artificial intelligence, and advanced control systems allow operators to monitor and manage electricity networks more efficiently than ever before. Instead of simply reaching the problems, future grid must anticipate and prevent them. One important reality is that there is probably not the unique solution for the entire continent. Because Africa is increasingly diverse, different regions possess different resources. Just look at the Democratic Republic of Congo and several Central African countries, for instance. They possess enormous hydropower potential. When it comes to East African countries such as Kenya, they have world-class geothermal resources, while North African countries benefit from some of the highest solar irradiation levels on Earth, and several coastal regions possess strong wind resources. So, the future of renewable energy sources on the African continent at large scale will likely be a combination of different technologies adapted to local conditions. Africans' universities, research institutions, technical schools, and engineering companies will all play a tremendously huge role in building the workforce needed to support that energy future. And after all this, there is another question that I personally find extremely important. What happens to solar panels or to wind blades after 25 or 30 years? What happens to millions of batteries when they reach the end of their useful life? A truly sustainable system should not solve an environmental problem while creating another one. The future is not just about producing clean electricity, it's also about designing systems that can be repaired, reused, recycled, and responsibly managed throughout their entire life cycle. These are questions that will become increasingly important as renewable deployment accelerates across the world. And I believe that they deserve at least as much attention as discussions around carbon emissions. But you, what do you think? Can Africa realistically build a 100% renewable grid? And on top of that, how should we deal with long-term sustainability challenges that are linked to renewable technologies? Let me know your thoughts in the comment, and if you enjoyed the video, don't forget to subscribe. Thanks for watching.